So welcome back to our Math405 class, and we'll go back from where we start. I think we start by the end of the slides for section 1.9. I wanted to show you a couple of things. So here we go again. Okay. So you remember, guys, we were able to find this plane which slides perfectly between the center of our data, right? And I just wanted to show you. I can share it probably with you my screen. Just wanted to show you before moving on to some new material. I wanted to show you how to do this using Visual. Yes, using Visual C++, Visual Python, and okay, so it's loading. I'll be able to show my application again. So here we go again. So here I've taken. So those who just joined, I'm showing again the same application we had before, but here I've entered the data based on two arrays. The first one contains the data about 20 employees instead of 10. So the first portion of it is exactly the same as we've seen before. So basically, we still have three rows. The rows are the experience, salary, and age. And here, this is the centered data matrix. And I have a second row, a second matrix, which is a little bit different. So let's assume it's from a different company. And we have here 24 employees. So we have basically 24 columns. And we have the same rows, one for the experience, one for the salary, one for the age. So what I wanted to show you here is that we could use the linear algebra function, which is SVD, to find directly the SVDs of both matrices at the same time. So here, for example, this function SVD, which takes as argument the A0 or B0, and it just calls the object LA, which is linear algebra. And what it does, it returns the matrices, the EU matrix, and the sigma matrix, and the V matrix for the corresponding SVD factorization. So in our case here, and this is just for the representation. So here, what I did is the computation. So the computation takes a little bit of time because we are in programming mode. And here, this is the plane again, but it fits. So we have more green points because we have 20 points instead of having just 10. Well, and you see other points, which are the blue points. What do you notice, guys? Now, one reason I'm showing you this is to make you observe the data before judging. What do you guys notice about the blue points? Here we computed the SVDs using the SVD function in Python. And we just did a representation of the plane obtained by the normal vector of the two left singular vectors U1 and U2 cross product. So to perform the cross product, guys, it's very easy. For example, here I've taken UA, UA1. So this is the first vector when I take the transpose of UA, and this is going to be the second vector, the one which corresponds to the second largest singular value. And if you perform the cross product, you get the normal vector. So basically, this is the one I've used. The component of NA, as you've seen in Math405, are used to write the equation of the first plane here, which corresponds to my image here. Now, what do you notice about the blue points, guys? Anyone has something to say? Sultan, are you trying to say something? Okay, so let me, just, you see that the green points, they seem to have a kind of linear relation, right? But what about the blue ones? The blue ones, they kind of don't have. So even though we can be able to find a linear approximation, okay, as you will see just right now, we can just also draw the second plane I could obtain, which is the one with the normal vector of the two first left singular vectors from B0. So here, as you've seen before, I perform the cross product of the two singular vectors I obtained, the two largest or the two most important singular vectors I obtained from UB, to obtain the normal vector NB. And I've used NB to write my equation. So here I can plot the plane, which represents the kind of rank 2 approximation of the data. Yes, Firas, go ahead.
I believe that we can't see the figure.
Okay, so I'm showing you the figure right now. Okay. You can see the figure? Okay. I'll share it with you right now because it's just combining. Okay. Okay. What about now, Firas?
Yes.
Okay?
Yes.
Okay. Sorry for that because it was compiling and it was shown in another window. Okay. So you see this is the second plane I obtained. Okay. Let me just move it a little bit up. So this is supposed to give a linear approximation of the blue points. Okay, and hopefully I will be able to just move it a little bit up like this. So you see, guys, what do you think? The blue points, I can't too much spread, and the linear approximation doesn't work fine. Okay, so it's not true that linear approximation works always fine. Okay. So compared to the previous case, it's not. It's a less. I mean, it's less good. Let's say linear approximation. So if I'm basing my approximation on a rank 2 matrix, maybe it's not enough. Get my point? Okay. So I'll stop sharing this. Okay. I'll upload the file which contains, everything that is done with the SVD function here and the cross product to draw the linear approximation. I would like to share with you something else. If you just be patient with me, I would like to share with you something else to show you an application which is quite interesting. And since we started this course, if you remember, we said that the kind of factorization we are performing, they are quite important in many fields. In some of the fields we've talked about were about compression of files, if you remember. Do you remember this, Shubha? First of all. Okay, so here we have an application of the SVDs in image compression. So here, the author, which is Hervé Abdi, is saying that, well, he's using SVDs, singular value decomposition, for image compression. For example, this is the image in figure 1, okay, which, as you see, displays 3 different colors, which are just white, black, and gray. Okay, and he's using the SVD to show that, well, the information contained in the image could be compressed or summarized using singular vectors of the matrix. So, for example, this image, as you see here, could be summarized in this matrix, which defines what? Every entry defines the level of gray that has to be shown in the image. Okay. So if it is black, of course, it's 2. If it is white, it's 0. And if it is, am I right? No, it's the opposite. If it is white, it's 2. If it is black, it's 0. And if it's gray, it's 1. If I'm right, yes. Okay. So one way to encode the coloring of the image. So you imagine each entry represents a pixel. So for example, for his own image, he in black and white, okay, he can say that he has like kind of 60,000 pixels to define, which means a 204 by 290 matrix, which is quite large matrix. And in the beginning, at the end, he's showing that, well, if he works with the image compression on his own image, this is the compression of his own image using 25 pairs of singular vectors, which is about compression rate of 80%. Okay, so for the human eye, it might be enough to compress images this way. Okay, so basically what he's showing here is that the different steps or stages that are provided once he adds the information about the next singular values or the next singular values. Okay, so he's even the images of accuracy, he's even everything. And he's showing just an application for singular. Well, for references, so if you're interested to read more, Hervé Abdi is a professor at the University of Texas at Dallas. Okay, so this is, I mean, the last part, 1.9. You've seen I've taken a lot of time to talk about SVDs because this is at the center of data science. Now I'll move on. Inshallah, if you don't have any question, I'll move on with the new material we have on from section 1.10. Okay. Can I proceed, guys? Are you okay?
Yes.
So we start talking today about 1.10, which is Rayleigh's Quotient and Generalized Eigenvalues. Next time, inshallah, on Thursday, I'm planning to talk about 1.11. And principally, I'll talk about tensors. And you can think about tensors. Tensors are kind of 3D matrices. Okay? So instead of having areas as matrices, you can have what we call tensors, which are 3D matrices. Okay, so what is Rayleigh's Quotient and what are generalized eigenvalues? So basically, we define Rayleigh's Quotient. This is just the outline. We define Rayleigh's Quotient as, depending on a vector x, as xt as x over xt x. If you think of it, xtx is just the norm of x, or the magnitude of x squared. And what it returns is that the maximum value for Rx will always be equal to the largest eigenvalue, lambda1 of S. Okay? So once you maximize the Rayleigh's Quotient, in fact, you're looking for the largest eigenvalue of S. And if you that maximum is achieved at an eigenvector, let's say x, which corresponds to Q1, I'm calling it Q1, then for sure Q1 solves the eigenvalue problem for S, of course. Okay? And in terms of value, R of Q1 would be equal to lambda1, the largest eigenvalue of S. Okay, I think it's pretty easy to think of the maximum of Rayleigh's Quotient as the largest eigenvalue for our matrix S. Similarly, you can think that the minimum value for Rx would be equal to the smallest eigenvalue of S. Okay, so what is interesting here is that Rayleigh's Quotient, once maximized, returns the largest eigenvalue. Once it is minimized, it returns the least eigenvalue. Well, the connection between what we've seen before and what we've seen now is that S is in fact a square matrix and could be written as before as the variance of this matrix, for example, for instance, ATA. So it is positive definite for sure. Sometimes are semi-definite because you might have entries which are equal to 0. And the Rayleigh's Quotient leads to the norm squared of A and the largest eigenvalue S, which is written in sigma form. Okay, so if you think of the norm of A as well as the norm of ax square over x square. Remember, this is the L2 norm, huh? This is the L2 norm in the previous slides, those for section 1.9. Well, you can think of it as the maximum of xt ATA, which is the way to capture, in fact, the norm of ax squared. And if you substitute ATA by S, well, you can see that, in fact, the magnitude of the LT norm is, in fact, equal to lambda 1 of S. So, in other words, what does it say, Shabab? It means that the absolute value, or the square root of the largest eigenvalue of S would be equal to the L2 norm, in other words. Okay? So we have one way to compute the L2 norm of our matrix S. You got it? So with this representation, you can see that the magnitude of A could be equal just as to the square root of lambda 1. Got it? Okay. Okay. So in other words, the norm of A, or the magnitude of A, is the square root of the largest eigenvalue of S, AT. So if you think of it now, sometimes I talk to my students and say, like, we've seen a new definition, a new concept, and I would like you to think, as a student, how can I be evaluated on this? How can be questioned on this? So if I ask you to compute the L2 norm of a given matrix, immediately you have to go to the Rayleigh quotient. Get my point? So in this way, a symmetric eigenvalue problem. So the eigenvalue problem is a solution to an optimization problem, which is the maximization of Rayleigh quotient. And in fact, as mathematicians, these are all problems, but there has been a generalization of this concept of Rayleigh quotient to include another matrix M between xt and x in the denominator. We call it the generalized Rayleigh quotient. Okay, and the solution to it, in fact, is the solution to a more general problem. Maybe for sure you did not see this in linear algebra course. We call it the generalized eigenvalue problem, which instead of putting I between lambda and x here in the eigenvalue problem, it writes what we call the generalized eigenvalue problem, where Sx is equal to lambda mx. And M lambda here, M is here supposed to be positive definite. So the maximum, again, as you've seen before, of the Rx, of the Rayleigh's quotient, would be the largest eigenvalue of the matrix M1. So sometimes we do have to deal with this because of the fact that we are in need to work on a more general case and a more general factorization. So basically, we can reduce how to solve this problem, the generalized eigenvalue problem. We check that this generalized eigenvalue problem could be converted to, with the right setting of matrices, could be transformed to an ordinary eigenvalue problem. Okay? So I hope you will be patient with me, guys, because this is just a simple, quite heavy mathematical development. Okay? I skipped most of it, believe me, and I've taken the most important part. Okay? So the idea here is to move on from a generalized eigenvalue problem to an ordinary eigenvalue problem, choosing the right h and the right y. Okay? How to do this? Well, to do this, the best choice is, well, since you know what is S and M, okay, you know these matrices, so you assume that we have a new matrix, we call it H, such that H is equal to M minus half, S, M minus half. Okay? If you remember, we've talked before about A half or A minus half. Well, you've just taken the square root when you talk to M to the power half of the elements. And since we've said that we have a positive definite matrix M, and if you're talking about M minus half, well, you just have to invert these entries. Symmetry here is saved. We choose the symmetric square root of M and M half, m inverse. And more than this, when you apply this factorization or this definition of H, you can see that you can, well, beautifully convert the Rayleigh's generalized quotient to the simple Rayleigh's quotient. So basically, when you maximize this R with respect to Y, what you get in return the largest eigenvalue for whom? You get the largest eigenvalue for H. Okay? You got it? So this changes the generalized problem as x lambda and x to an ordinary symmetric problem, which is an ordinary eigenvalue problem. And sometimes we don't need to work on we need not to work on the ordinary eigenvalue problem. We work on the generalized eigenvalue problem, and we have a way to move backwards to an ordinary setting. Okay, so let me finish with a couple of things. So if S and M are positive, so then H would be positive definite. And the top eigenvalue lambda 1 and eigenvector y1 of H have a way to connect to the top eigenvector x1 of M1S, and you can write x1 as m minus half lambda. Okay, so we'll see later on, inshallah, an application to this numerically on how to get it. So an application to this. So here we have this, what we call this new problem, Shabab. What did I say? This is the generalized eigenvalue problem. Generalized eigenvalue problem. Okay? Yeah, Muhammad, go ahead.
Sorry, but for the previous slide. So the idea is when we include, so we introduced a new matrix H that includes both S and M.
Yes.
Okay, thank you.
Yes. Yes, and this matrix, thank you for the question, Muhammad, that matrix H help us move from the generalized eigenvalue problem to an ordinary eigenvalue problem again. But what you would obtain from that needs another conversion to be written in terms of the maximum eigenvalue for M1s. So the goal of the generalized eigenvalue problem is to find eigenvalues for whom? For M1s. Okay, so let's see with the numerical application. So with this numerical application, I have two beautiful matrices, S and M. As you can see, both matrices, this is positive definite, right? You know this, صح? Why? Because you see the leading determinants. The first determinant here is 1, the second is 2. Similarly, you see that S is positive definite because you get first determinant here is D11, which is 4, and the second one would be 16 minus 4, which is 12. Okay? Both are positive definite. And if you work on the generalized eigenvalue problem directly, there is a way to do it. So basically here you need to understand what to do. Previously, Shabab, and with the ordinary eigenvalue problem, instead of having I, we had I, right? So that's why when we were solving the ordinary eigenvalue problem, we've put here I instead of M. You got it? So the only difference is that the generalized eigenvalue problem now extends this, and when you seek the eigenvalues or the generalized eigenvalues, you'll be looking for the determinant of S minus lambda M. Okay? And if you're looking for the determinant of S minus lambda M, well, here for this case, it's very easy. You get these two beautiful eigenvalues, which are 3 plus M minus 1 root of 3. Okay? So basically, we know already the answer. So 3 plus or minus root of 3 are in fact the solutions to the generalized eigenvalue problem. But so this is one way. This is the first way to do it, is to solve the problem directly. But sometimes solving it directly is a headache. Okay, so we need to use the transformation. We need to use, as you said, Muhammad, this matrix H, which writes as n minus half S n minus half. Well, so you see this S is between Well, beautiful. There is no problem. So here I'm basically writing h. Now what about m minus half? So let me first talk about m half. M half would be written as just as the square root of the entries here. So it's 1, 0, 0, and root of 2, right? So if I invert every component here, I get m minus half. So get 1 over root of 2. Got it? And on the other side, I get the same matrix, which is m half. So basically, this matrix is what? This matrix is H. Now I can work with H here using the ordinary eigenvalue formulation. And if I work on this matrix, basically I'll be solving just a second degree equation. I get these two beautiful eigenvalues. So these two beautiful eigenvalues are eigenvalues for H and generalized eigenvalues for the which matrix for the generalized eigenvalue. So they are eigenvalues for S minus 1m. Okay? As we said before, these for m minus 1s. I'm sorry. Sorry for the misspelling. Okay? So we got the first way. First way. Sometimes the first way doesn't work. Working directly on the generalized eigenvalue formulation doesn't work. So we better seek another way to do it, which is much more simple, which is the identity matrix. And the second way finds the same answer. Is that okay, guys? A simple application. If you check the problem set in corresponding to 1.10, you have more diverse set of questions. Any question, or can I move forward? Okay, I'll move forward if you have any question. Please let me answer. So once we've talked about generalized eigenvalues, well, they go together. We have to talk about generalized eigenvectors. So once you obtain the generalized eigenvalues from the generalized eigenvalue problem, we can compute what we call the generalized eigenvectors. Well, let's have some thoughts. So a crucial fact about symmetric matrix S is that any two vectors are orthogonals. Any two eigenvectors are orthogonals, and you've seen that before. But does this extend to the solutions of the generalized eigenvector problem? So suppose that X is the generalized eigenvector, which takes the generalized eigenvalue formulation and places X here. Okay? Well, what we can show is that the generalized eigenvectors here are not orthogonals, but they are what we call M orthogonal. What we mean by M orthogonal is that when you place M between them, you get a 0. You may not get a 0 when you perform the dot product x1 by x2, or what we call also the Cartesian product, but you get a 0 when you put M between. So the generalized eigenvectors are what we call M orthogonal, which is a new notion to us. M orthogonality. So, for example, here, how to find questions for you, how to find the eigenvectors x1 and x2 in the previous example, and how to show that they are M orthogonal. What do we need to solve to do that? We said before that we have two eigenvalues, which were 3 plus or minus root of 3, okay? And basically, we have the matrix, which is H, which is 4 minus root of 2, minus root of 2, 2, okay? So if you would like to write the, to solve the generalized eigenvector problem, I'll share with you my whiteboard. So, so if H is equal to 4 minus root of 2, minus root of 2, 2, how can I write the generalized eigenvector problem? I'll write it as Hx equals lambda x, am I right? See here, I'm using H itself to find the eigenvalue. So if lambda is equal to the first eigenvalue, let's suppose, it's 3 plus root of 3. right? If I'm looking for x equal to AB. I solve, I get on the left side for a minus root of 2b equals lambda a in general. And here I get minus root of 2a plus 2b equals lambda b. Okay, so if you write the kind of the matrix that summarizes the information here, I'll have 4 minus lambda. Anyways, I have minus root of 2. On the side, I get a 0. And here I have minus root of 2, whatever happens, and have 2 minus lambda. Okay. So basically, I'm solving this linear system. So if I take the first lambda 1 here, I'm going to get how much? 4 minus 3, which is 1. So I get 1 minus root of 3, square root of 2, minus square root of 2. And basically, I'm going to get 2 minus 3 minus, so I get minus 1 plus root of 3. Am I right? Okay. From here, I just have to solve and get the correspondence between A and B. Okay, so you can just proceed from there. Okay, so you can continue from there. Sure. Okay. So you can solve it as you do the same for lambda 2, and you get the two solutions, x1 and x2, and you can show that in fact x1 transpose times mx2 is equal to 0. So basically, the two generalized eigenvectors are m orthogonal. Okay. Right. Now I'll move forward a little bit. To a new principle, which is so we talked about this. So since we've talked about generalized eigenvalues, generalized eigenvectors, well, what happens now if the n is positive semi-definite but not invertible? And does this concept of generalized problem, in fact, extend to the SVD? We've seen SVD as the principal component analysis main feature, right? Okay. So what does it mean to allow for a second matrix M in our problem? So now we talk about what we call the generalized SVD problem. Generalized SVD problem. Well, I give you just the scheme, guys. Just what is important. The primary purpose here of the generalized SVD is to factor a set of matrices at the same time. So in our case here, we'll talk about factoring two matrices A and B at the same time, which is beautiful. So if you have two different samples or two different populations of the same problem, okay, you can use the same matrix to a common matrix to factorize the two data matrices. Okay, so we call it the goal of the SVD is to factor A as U times sigma VT. So consider that we have two matrices A and B, which are tall and thin. Usually we say tall and thin. Why? Because we have a huge number of individuals in every population, but a limited number of features. Like we've seen in the salary problem, we have age, salary, experience, and we have a very high number. We could have a very high number of employees. So the sizes of these two matrices in our case are MA by N and NB by N. So what they have in common is the number of features. Like in the case I displayed in the 3D figure, I have two populations. So the number of features are 3, but the number of items or the number of individuals in my populations are different. And let's assume that we have S, which is equal to ATA, and M equal to BT, which are, of course, going to be found to be positive definite by definition. So in its full version, in fact, the GSVD allows for the two matrices S and M to be singular, which solves the problem for the generalized eigenvalue problem. So if you go backwards to this question, what happens if m is positive definite? Well, the solution to this is to talk about the generalized SVD. And we talk about the generalized SVD. In fact, if it's in terms of manual computation, it's quite complicated. Okay, so but let me sum it and say that it allows to find a common matrix Z that writes A as equal to UA sigma AZ and B equals to UB sigma BZ. There are a couple of properties. First of all, that UA and UB are two orthogonal matrices. So if you multiply UA by its transpose, you kind of have the identity matrix. Similarly, so remember when you say UA is an orthogonal matrix when you have UAT times UA is equal to I. And similarly, you will have UBT, UB equals to I. Got it? More than this is that sigma AT transpose times sigma A plus sigma BT transpose times sigma B equals to the identity. Okay? And believe it or not, guys, look how good, how fair am I. I'm not going to show you how to solve it manually. It's quite complicated. But what we do is to use a couple of libraries we have available. So now, how to do it, first of all, just to understand it. Z, which we are looking for, is going to be an invertible matrix of size n. So it's a square matrix. And to find Z, what we can do is that, don't forget that we set S as ATA and M as BTB. So we could substitute with the factorization you had. This was A, and this is going to be AT, so? And don't forget, we said that UAT times UA is I. So basically, when this writes as I, you can see that S is ZT times sigma T, sigma A, Z. And similarly for M, you can write it the same. So basically, since when you sum up, you get what? You get S plus M equals ZT times what is between is sigma A plus sigma BTB, which is I itself. So this is going to be I, and you get Z. Okay? So in fact, I'm not going to move too much, but in fact, this formulation, we've seen it before. This is what we call the spectralization. So we kind of we are able to say that in fact is gives a spectral factorization for S and M at the same time. And what is beautiful here in linear algebra is that any two positive matrices can be diagonalized using kind of spectral factorization with Z, with the same common matrix Z. Of course, the entries in the sigma, of course, are going to be different. And basically, the only difference with the previous spectral factorization case is that we have to scale Z so that we get the sum of sigma AT, sigma A plus sigma BE equals to I. So I'll show you now how to do it. Okay? The thing we have here is that we could be able to show how to do it. I hope you'll like this. So to do that, first of all, let's suppose in my example here, I'm saying that I have two data matrices, which are A and B, and just for simplification, I've taken matrices of the same dimensions. Okay, so I have AT, which is 1 0 1 0 1 1. So this is A transpose, and B is 1 0 minus 1 0 minus 1 1. So basically, we have two features. If you just transpose, have three rows and two columns. So if you compute S, which is AT, and M, which is BTB, you get these two beautiful positive definite matrices. Okay, and to do that, to compute that, I'm referring to the GSVD function in MATLAB. Hopefully, you have access to MATLAB, guys. If you don't have access to it, I'm pretty sure you can arrange to do that. Otherwise, have a common and flying license at KFUPM. When you visit the MATLAB website, you just enter your credentials, your KFUPM email, and you will get the confirmation that you have access to it. Okay, so how does it work? The function to call is this, is it GSVD of two matrices AB, and what it returns the 5 matrices we're looking for. Basically, here they are in order, so I'm calling them UA and SA, and you see that in that case, UASA Z, which always at the center and third position, gives the first factorization. UBSB helps writing B as UBSBZ. So for instance, here with the MATLAB encoding, I'm able to get this. So I'll share with you my MATLAB window. And also, if you read R, it's from now on, I think it's kind of the same product. So basically, you have it's very common. Yeah, this is it. So basically, you have kind of the same functions. Okay, so I'll scroll with you what I just did. Okay, so basically here, when I define it here, so able to see this, Shabab? Okay, so this is how I have the matrix in MATLAB. So basically, this is the matrix A. Sorry, this one. Okay. This one has, you have to put these kind of dots, semicolons between the rows. So you get the first matrix A, and I'm just making sure that I define S the right way. So S is ATA. It is displayed automatically. Okay, and here I'm entering B as 1, 0, 0, minus 1, 1. So I get my B displayed correctly. So this is M, which is transpose B times B, okay, or BTB. And I'm just calling the GSVD function here, GSVD of AB, gives me exactly what I needed. You have the 3 by 3 matrix UA, the 3 by 3 matrix UB, Z, which is kind of root of 2 minus root of 2 minus root of 2 minus root of 2, and you have the two generalized singular values in sigma A and sigma B. So these are the, and here I'm verifying just that UA sigma A Z gives exactly A, as you see, 1, 0, 0, 1, 1, 1, and I'm also verifying that this factorization works well also for B. I have UB sigma BZ, which is exactly the same. Well, the question here maybe that could be asked, why we don't have that feature in Python directly? Well, there are people that coded a package, but I honestly didn't have the time to download it and install it on Windows. I'm pretty sure it works much better on Linux, so I didn't do it right away. But with MATLAB, it's very easy to use. Okay. Any question on that, guys? Okay, so now to finish, to close this this talk about generalized eigenvalues, generalized eigenvectors, generalized singular values. The last part we'd like to think of it is how to, like in the previous case I've shown guys at the end of at the beginning of today's lecture, we have two individuals. We have individuals belonging to a population. Okay. How to determine, once you picked an individual, how to determine to which population or subpopulation it belongs. So let me rephrase it. Okay. So suppose you have here samples from two different populations. Okay, and these are mixed together. So suppose you have a sample of employees that belong to that population of employees, and we would like to, in studying the features of the sample, you would like to know or to decide to which population it belongs. So we know the basic facts about each population in large. For example, in our previous case, We know the basic facts about average salary, the average experience, the average age. And if all these samples are mixed together and we pick one, how do we tell if it probably came from population 1, so from company 1 or from company 2? Okay, we've seen like in company 1 there is a high correlation between age, experience, and salary, and the second one maybe not. Okay, so for example, in the case of child age, we know the features. So we want a rule to discriminate between two populations, and to do this, it is normal for machine learning to use what we call a feature vector. So a feature vector, kind of a vector that carries the age, the height, and weight of each individual, or for the whole sample. So if a sample has a feature vector f, and you find it, so to which population does it belong? In fact, Fisher's linear discriminant answers that question. And to do that, he uses this formulation. Okay, and can you tell me what does it remind you of? It looks like a Rayleigh quotient, صح? So he kind of tries to find the maximum distance between the maximum vector that maximizes the distance between the populations. So if the mean average of the population I is the vector mi, which carries the age, the height, and the weight, so this is the feature vector. Similarly, you can define a covariance matrix for each population. Okay, and this defines a matrix sigma 1 and sigma 2, variance matrix for population 1 and population 2. And you work on the Rayleigh quotient, rephrase it. And what is said is that if you maximize the Rayleigh quotient, okay, based on your sample, okay, so what does it say? If Vt is the solution to your Raleigh's maximization problem, okay, if it is larger than C, then you can say C is a fixed preset to a certain value. Then you can say that it belongs to the first population, otherwise it belongs to the second population. So, in fact, with the Raleigh's quotient here, we convert the generalized Raleigh's quotient problem. Okay, we use the generalized Raleigh's quotient and the V that maximizes this quotient can help us decide on which population or subpopulation our sample belongs to. Okay, so basically that was the main idea. So to summarize, what Fisher's linear discriminant does is that we have two classes of points in three-dimensional feature space, like we've seen before at the beginning of the lecture, and we try to separate them by plane, which is maybe not possible. And Fisher proposed one reasonable plane to do that. And at the end of the course, we'll see how neural networks succeed in using more than planes. They use separating surfaces to separate samples. Okay? So thank you very much for listening. This is what I had as material for today. Okay? And hopefully, inshallah, we'll come back to it to detail every part in the next assignments and exercises we'll have. There are a couple of questions I had to answer. I made all the links I shared with you for the lectures recordings public. So hopefully from now on there will be no complaints. And I'm setting a kind of YouTube channel for our lectures also to make it available for everyone at all times. Okay. Any questions, Shabab? Anything you would like to inquire about? Yes, Abdurrahman.
Sir, did you decide when the major will be?
Yeah, good question. Thank you, Abdurrahman. So last time we said it's the 8th of October, but at the end, after some of you left, some said that maybe it's better to delay it. So what do you think? It was the 10th of October, but some say maybe it's better to postpone it or delay it. So you still agree on the 10th, Shabab, 10th of October?
For me,
anyone against? Okay. Ziad? Ziad, I would like to delay it, but if you postpone it, we'll have more material. You get my point, Shabab?
How much more material,
It's
Doctor?
not always. At least 2 to 3 more sections, yeah, Ziad.
Okay, Doctor, but at least we can study more.
لا.
So look, I'm pretty sure yes. You see, there is a division here. We cannot agree on. Okay.
Doctor, the problem with the current
Yes,
date, we don't have enough time to study at all.
Yeah, exactly.
Okay.
More
So
time.
look, can we divide the apple in two? I'm pretty sure no one is going to agree. Okay. So let's see. So the first proposition was 10, and some guys said also 17, right?
Most of us said 17 actually.
I don't know how to judge. I don't know how to judge most or no. So you cannot even, Khalid, this will generate a lot of problems and we have to settle this. What about, guys, what about putting it on the 13th or the 14th October?
It will be good for me.
Okay, so it's between, guys, okay? So for example, it's not the 10th, it's no longer a weekend, okay? So nobody can complain. And it's no longer the 17th, okay? So I propose
14?
you have, Sultan has a major on 14. So I'll put it the 13, okay? Are you okay with the 13, ya shabab? 13 October.
Sir, you can, I think,
So
here you can make survey.
Okay. So I'll put it the 13 and ask everyone to send me لا يا سلطان قلنا we try to divide the apple in two. So not the 17th, not the 10th. I'll put it between. So at most we have one more section. Okay. So we'll put it the 13 by night as Sultan. We're trying to accommodate you. You have a major on 14. Okay. So we'll put it on the 13th, inshallah, and everything will be fine. Okay. So 13th, which is a Tuesday night, 13th. Okay, so probably it's going to be from like after Isha, yani from 8 to 9:30 p.m. And we'll do a rehearsal just a couple of days before on Thursday on a sample quiz. Okay. Okay. The material probably, guys. So the material will run from 1.1 ya Sulay ya Abdulaziz till probably till 2.2. Okay. Hello? Yeah. Shabab, see you in good shape. Take care. So 13th decided, inshallah, and hopefully it's going to be fine for everyone. Nawaf, yalla, last question.
Doctor, the slides here are not exactly as the same in the Blackboard. In the Blackboard, you missed the example in slide 10, I think.
You mean which slides? The one for today's lecture or the previous ones?
No, for today's lecture. This slide.
Did I upload? Did I upload it?
It missed this
okay.
slide.
Okay, I remove it. I'll change it. Thank you very, very much, Noor.
Okay, thank you, Doctor.
Okay, guys. So see you in good shape. Thank you very much. Have a wonderful